This is part 3 of my series on motion in a central force field. And as always, let us go for a quick recapitulation. A central force, as you all know, is a force which is always directed towards a fixed center and has a magnitude which depends only on the distance from the center. We have also seen earlier that a two-body problem can be effectively reduced to a one-body problem which involves a central force, and separation between the two particles there, r vector, is what stands in for the distance vector here, and the only difference is that the mass has to be replaced by the reduced mass. Mu is m1 m2 by m1 plus m2. And if you look at the equations of motion, the equation for cross-radial motion can be easily integrated to give you r square theta dot equals L over mu, where L is the magnitude of the angular momentum. And if you use that in the radial equation, you end up with a radial equation which is effectively a one-dimensional equation, mu r double dot equals f of r plus L squared by mu r cube. We had also seen that this equation can be integrated directly to give the conservation of energy equation in the form which involves only r. Half mu r dot square plus an effective potential energy equals the total energy. The effective potential energy is the actual potential energy plus an additional term which really is half mu r square theta dot square, but which, using our conservation law which we had already established, works out to be L square over 2 mu r square. So U effective R depends on the initial conditions, but apart from that, it is a function of R and R alone. In the last lecture, we had analyzed the motion of a particle in a central force field based on this U effective. In particular, we did a graphical analysis where we talked about a situation where if you have a potential which is attractive and falls down to large negative values but not too fast for small r, you get an effective potential which has a bump like this, a minimum, if the energy of the particle is exactly equal to the minimum of the effective potential. Then you have a circular orbit. For energy slightly more than that, you have two turning points and you have an orbit where the radius goes from a maximum value r max to a minimum value r min. And in this particular case, if you have an energy which is too high, positive energy in this case, you will have only one turning point where the radial motion will turn back, and this actually implies that the force for this particular situation will admit of an open, unbounded orbit. We had also seen the different kinds of effective potentials that you could get for other kinds of potentials. Potentials which are attractive and fall off to minus infinity too fast, or attractive and rise up to plus infinity, or repulsive. Now, in each of these cases, we had seen that an analysis based on the effective potential tells us exactly what kind of orbits we could have. Turning back to a situation like this, where the effective potential energy has a minimum, we do see that if energy is exactly equal to U0, the minimum value, of course we have only a circular orbit. But if energy is only slightly larger than that, then the radial motion can be approximated by a simple harmonic motion, simply because close enough to a minimum, every smooth function essentially looks like a quadratic function. And we figured out that the time period for that radial motion from r min to r max and back again to r min is given by twice pi times the square root of the reduced mass mu divided by the second derivative of the effective potential evaluated at r0. Note that r0 can be evaluated by setting the first derivative of u effective to 0. And because U effective is assumed to have a minimum at R0, U double prime effective at R0 is positive. And so there is no problem with this expression as far as the sign is concerned. Let us now make use of this formula to find out the time period for radial oscillations for orbits which are very close to circular in the case of a potential that we know is of great importance. This is nothing other than our familiar Kepler potential. The standard inverse square law of force would lead to a potential U of R equals minus K over R, and for an attractive case, as is the case for gravitation, capital K would be positive. So what kind of time period would you expect the radial motion to have for such an orbit? And a very important question to ask would be, how does this time period actually compare with the time it takes for the particle to go all the way around? We will see that the answer to that question has deep significance. First, let us carry on this calculation using our formula. We start with the U effective of R, which is simply U of R minus K by R plus the centrifugal potential barrier term L square by 2 mu R square. A simple calculation which tells us that the derivative is given by K over R square minus L square by mu R cube. Again, this result itself should be pretty familiar. After all, the negative of this is the net effective force acting on a particle, at least as far as radial motion is concerned. There you have the minus K by R square force, which is, of course, the standard inverse square attractive force. And added to that, you have the centrifugal barrier force term, plus L square by mu R cube. We will not stop here, however. We will carry out the derivative one step further. And that will give us minus 2K over R cube plus 3L square by mu R to the 4. Now, what we need to do is evaluate U double prime effective at R0, where R0 is the radius of the circular orbit. But that means we have to find out R0 first, and that is easily done by setting this U prime effective R to 0. So that gives us the radius of the circular orbit. The equation we have is K by R0 square minus L square by mu R0 cube equals 0, which of course implies that R0 is given by L square over mu K. Of course, the right hand side is a constant, as it should be, but it is not a constant independent of the initial conditions, which is again reasonable. How big a circle will be executed will of course depend on the initial conditions. The L here hides inside it the fact that the initial value of the position and velocity go into it. So this is an initial value dependent quantity. But this particular combination L square over mu K is something we are going to meet over and over again in the theory for the Kepler orbits, not just a circular orbit. But at this stage, this is just the radius at which you will get a circle. What happens if you perturb the motion a bit? That is, the motion is now slightly away from a circle. We already know, at least from Kepler's first law, that the answer should be an ellipse, and we expect the ellipse to have almost equal semi-major and semi-minor axis, that is very low eccentricity, almost a circle. By the way, almost each and every planet in the solar system is an example of this. They do execute elliptical orbits, but the elliptical orbits are actually pretty close to circles. Eccentricity is rather low. However, we do not really need to know the exact shape of the perturbed orbit to find out the time it takes for the radial oscillations. All we need to do, of course, is to calculate the second derivative of U effective at R0. And if you do that, you just plug in R0 for R in this expression, you get minus 2K over R0 cube plus 3L square by mu R0 to the power 4. And taking the minus 2k by r0 cube common out, you get this expression within the brackets. This may begin to look a bit complicated, but notice that L square is actually equal to mu k r naught. And if you just use that, this bracket simply becomes minus 1/2. And in addition to this minus 2 out here, it gives you plus k over r0 cube. Of course, this turns out to be positive as we expect. Perturb a circular orbit for the Kepler problem slightly. The motion stays bounded. In other words, circular orbits are stable. Now, the time period is easily calculated. This is the radial time period, and it's given by 2 pi over square root of mu divided by u double prime effective at r0, and that's nothing but 2 pi square root of mu r0 cube by k square root. So far, so good. We have got t radial. We need to compare this with the time it takes for the particle to go all the way around. And we are just going to use the circular orbit's value for that. And that's simply t theta, 2 pi divided by the angular velocity. For the circular orbit, of course, the angular velocity is a constant. And it is given simply by L over mu r0 square. So, if you just put this deliberately into a square root, you get 2 pi square root of mu square r0 to the power 4 by L square. Of course, the square root here is simply because I will ultimately want to compare this with t radial. Now, we have already seen that L square is mu r naught k. And just using that tells you that t theta, the time it takes for a complete orbit all the way around, is given by 2 pi square root of mu r0 cube over k. Exactly the same as the radial time period. So by the time the distance from the center changes from a minimum to the maximum and then back to minimum, back to its original value, the angle turns all the way round through 2 pi. And this hints strongly that what we have here is a bound orbit, which is closed. That is, it starts and ends at exactly the same point. The equality of these two time periods tell us that. Now, you might be slightly skeptical here because we have used the time period for the circular orbit for t theta, the time it takes for theta to go all the way around through 2 pi, even for this slightly perturbed orbit. Later on, when we derive a related theorem called Bertrand's theorem, which is a much more general statement of this problem, we will actually give you a more precise proof of this fact. But this actually is quite accurate as it stands. Now, note that the result that we have also hints at Kepler's third law, since the square of the time period is proportional to the cube of r0, as you can see here. Of course, this is only for orbits which are very, very close to circles. Kepler's third law is valid for any orbit, at least any orbit in the Kepler problem. We will also show that exactly later. But note one thing, not only does this hint at Kepler's third law, it actually also says that the original statement of the Kepler's third law, that if you take all the planets in the solar system, the square of their time periods is proportional to the cube of their semi-major axis, is actually an approximation. Since the so-called constant that is sitting between t square and r0 cube involves mu over k. Now, k is g m1 m2, and if mu had simply been m1, the mass of the planet, then this result would simply have been 1 over gm2, something which is the same for all the planets in the solar system. However, what you have in the numerator here is mu and not m1. So what you have is m1 m2 by m1 plus m2 in the numerator. So the ratio is not actually 1 over gm2, it's actually 1 over g m1 plus m2. So the mass of the planet also comes in the expression, different planets, of course, have different masses. So M1 plus M2 will be slightly different for each one of them. However, the Sun is so much more massive than the planets that M1 plus M2 is almost exactly the same as M2, which is why when Kepler formulated his law based on observations by astronomers such as Tycho Brahe and himself, he did not see any difference in the ratio between T square and R0 cube from planet to planet. But if the masses of the orbiting objects were close to the mass of the central object, you would actually see a significant difference. Now that this particular example has convinced you, hopefully, that the notion of the effective potential is useful not only for doing qualitative stuff, that is determining the nature of the orbits, whether they are bound or not, etc., but also for quantitative work, let me now turn to the question of using this idea of the effective potential for a much more drastic amount of quantitative work, actually solving this problem as completely as possible. Please note, however, that this does not mean that we are not solving this problem from the equations of motion. After all, the law of conservation of energy and the notion of effective potential that we have used here are both consequences of the equations of motion. The advantage here, of course, is energy being a first integral of the equations of motion, we have landed up with a situation where we only need one further integral to work out the answer. The way in which this works is the following. You start with the statement about conservation of energy, half mu r dot square plus effective potential equals E. Note that in this whole expression you have an r dot. Everything else depends either on the initial conditions. E, of course, depends on the initial conditions. And U effective has an L in it, which depends, of course, on the initial conditions. But other than that, the only dependence of everything else in this equation is on R, which means we can immediately solve this equation to find out R dot, the rate at which R changes with T, as a function of R and R alone. So dr dt can be easily figured out from this by moving the U effective R to the other side and dividing by half mu and taking the square root. And we end up with this expression where what is important is the right hand side depends on R and R alone. One important issue, of course, is that you cannot figure out whether dr dt is positive or negative from this, that is whether the radius is decreasing or increasing. That information is not there in the law of conservation of energy. After all, because it involves only r dot square and not r dot, it cannot tell you whether you have a plus sign or a minus sign there. But this again should be pretty familiar to all of you. Whenever you use conservation of energy, even for a one-dimensional problem, to find the velocity of a particle, you do not really get the velocity, you just get its magnitude. The sign cannot come out of conservation of energy. It only can come from the initial conditions for the problem. Now, modulo the plus or minus sign, which can be figured out from the initial conditions, this equation is really very simple to solve. All you have to do is to bring all the variables of the same type to the same side, that is, separate the variables out. Here is triviality itself. All you have to do is write this as dt equals dr divided by this quantity on the right here, which is a function of r alone. And once you have done that, you can immediately integrate dt to get t minus t0 equals, or t equals t0 plus the integral of dr divided by r dot. And this dr by r dot expression has a plus or minus sign, the same plus or minus sign that we had here. And the integral has to be carried out from r of t0, the value of r at the initial time, to the r at time t. And we have just rewritten this here slightly by expanding out the U effective R and showing explicitly the original potential energy which describes the system and the L square by 2 mu R square centrifugal potential barrier term. This is the full expression for T. So this ultimately gives you T as a function of R, which you can then invert to get R as a function of T. So the job of finding out the radial distance of the particle from the center has been reduced essentially to calculating an integral. This is exactly what we mean when we say that we have reduced the problem to quadratures. There is only one integral that you have to evaluate. After that, you have got your solution. Of course, experience with calculating integrals should have already told you that not all integrals are easy to calculate. Some of the integrals cannot even be ever written down in terms of simple functions, but that is really not the issue here. The issue here is that once you have this, you have a prescription to clearly figure out exactly how R of t is. If you can evaluate the integral in closed form in terms of known functions, well and good. If you can't, there are always approximation techniques to fall back upon, or if all else fails, you can always plug in the integral in a computer and evaluate it numerically. But at least the job of solving R of t has been completed in principle. Of course, the specific form of R of t will depend on the potential U of R as well as the conserved quantity L, and we will see applications of this formula later on. But let me also point out that this does not tell me all about the motion. This just gives me R as a function of time. If I also have theta as a function of time along with it, then the two together will give you a complete description of how the particle will move as a function of time. In fact, now that we have reduced the problem of calculating R of t to quadratures, evaluating theta of t is actually just one more integration away. Notice that theta dot is given by L over mu R square. So if you know R of t, you actually know theta dot as a function of t, and therefore all you need to do is integrate this with respect to time from t0 to t to get theta t equals theta at t0 plus this integral. So once again, the problem of evaluating theta has now become a problem of evaluation of an integral. So the entire problem has been reduced to quadratures. Of course, while it is all very nice to say that we have reduced the problem to quadratures by essentially reducing the whole problem to evaluation of a couple of integrals, calculating the integrals themselves may be quite a difficult task. Sometimes this may be much more information than we need. For example, very often it may be easier to calculate R as a function of theta directly rather than R of t and theta of t separately. Of course, knowledge of R of t and theta of t is essential if you wanted to know exactly where the particle is at each instant of time. If on the other hand all you were interested in was a trajectory, then knowledge of R of theta would be enough. Of course, if you did get R of t and theta of t separately, you could eliminate t between the two and find R as a function of theta. However, it is actually easy to directly calculate R as a function of theta, and for that all you need to do is take a look at this equation. This is just elementary calculus that d theta dr is nothing but the ratio of theta dot over r dot. But now theta dot is known to be L by mu r square. So you are dividing L by mu r square by r dot. Remember though that r dot is actually known already. R dot is up to a sign given by root over 2 by mu E minus U effective at R. So, dividing L over mu r square by this gives me an expression which depends on R and R alone, and therefore it's easy to separate the variables once again here. Write d theta as dr times this factor which is a function of only r. And now it becomes very easy to integrate this. I've mixed out theta 0 here. So theta equals theta 0. The plus or minus sign here comes simply from the fact that r dot comes with a choice of both signs possible. And after that you just have to evaluate this integral. L dr by r square, the mu in the denominator enters a square root as mu square, cancels with 2 over mu here to give you a 2 mu. The rest is sort of obvious algebra. So now we see that determining theta as a function of r has been reduced to a single quadrature. All you have to do is evaluate this integral and you directly get theta as a function of r. And it sometimes happens that it is actually easier to evaluate this integral explicitly compared to the integrals for r of t and theta of t that we had mentioned earlier. Indeed, the Kepler problem is actually one such problem, where finding out theta as a function of r is reasonably simple. We are going to do that, and we are going to show you other ways of evaluating theta as a function of r, or the other way around, r as a function of theta. But evaluating r as a function of t and theta as a function of t are both quite difficult, non-trivial problems. Now, one thing that this particular equation helps us to do, even if we were interested in the full trajectory dynamically, that is, even if we needed theta of t, r of t, we would still make use of this particular equation to figure out one very important feature of the orbit. Would the orbit be closed or not? For that, we need to calculate the apsidal angle. Remember, the apses are points of minimum and maximum distance from the center, which essentially are the radii r min and r max for a bound orbit. And theta a, the apsidal angle, is the angle between the lines joining those 2 points with the center. So from the equation that we had written down, we can figure out, and here we can ignore the overall sign, that theta a is simply the integral from r min to r max of this integral, L dr by r square, root over twice mu E minus U effective r. The picture alongside shows you exactly what we mean by theta a. This is the pericentron, one of the apses. This is the other apse, the apocentron, the furthest point. These are the 2 apsidal lines, and this is the apsidal angle. The apsidal angle is actually very important for one very obvious reason. If theta a divided by pi happens to be rational, then after a sufficiently large number, possibly, of radial oscillations, you will find that radial oscillation and this cycling of theta, which happens every 2 pi, would coincide, and therefore you will land up at exactly the point where you started. This would mean that the orbit is a closed one. If theta a by pi is irrational, then no matter how long you waited, you will never have the radial oscillation and the angular libration going round and round coincide, and therefore you will never have a closed orbit. Note that this is different from what we did a while ago, where we talked about oscillations in the radial direction for small departures from a circular orbit. This equation that we have written down here is actually valid for all bound orbits. Let us now directly calculate this theta a from the integral for a couple of potentials which are of great importance. The very first one that we will pick on is, of course, what else? The Kepler potential. So u of r is minus k over r, and u effective r is, of course, minus k over r plus L square by 2 mu r square. Now, for a bound orbit, we have E, the total energy, as a negative quantity. And Rmax and Rmin are the two roots of U effective R equals E. From what we had argued in the last lecture, it should be obvious that you will have two roots for this equation U effective R equals E only if the energy is less than 0. For positive energies, you have only one turning point and the orbits unbound. So, U effective R equals E essentially means this is the equation you have to solve to find out Rmax and Rmin. Now, this equation can be rewritten in a slight manner. You just multiply through by R square and divide by E to rewrite this equation in the form of this quadratic in R square. And because the two roots are Rmax and Rmin, and also because the R square here has coefficient of 1, this is nothing but R minus Rmax into R minus Rmin. This form will be useful for us soon. Now, theta a, the integral that we have to do, is basically an integral from Rmin to Rmax of LdR by R square square root of twice mu E plus k by R minus L square over 2 mu R square. Taking a cue from what we had done here, that is multiplying by R square, I will just move one of the R's inside the square root and take square root of 2 mu times minus E out as a constant. Note that minus E is actually the positive number here. So if you had taken plus E out, of course you would have had R minus Rmax times R minus Rmin under the square root. But because of an extra minus sign, we really have Rmax minus R times R minus Rmin under the square root here. This is what you need to integrate. And of course the switch of the sign is a good thing because Rmax minus R and R minus Rmin are both positive quantities when R is within this limit of integration. So there will be no issues with a negative square root here. Now this integral is one that can be evaluated pretty easily. This is the standard integral and its value happens to be pi over square root of Rmax times Rmin. So the final result for the apsidal angle is L over root over twice mu times minus E times pi divided by square root of Rmax times Rmin. But note that Rmax and Rmin are nothing but the two roots of this quadratic equation. So the product of the roots must be simply minus L square over twice mu E. So this expression works out to be pi times L over root over twice mu into minus E, which was already there, times 1, of course the pi has been taken out here, divided by the product of the roots, square root of the product of the roots, which is minus L square by twice mu E, and everything cancels out. So we are left with theta a being simply pi. Note that this is quite different from the calculation that we had done earlier using the second derivative of U effective at R0. That was for small departures from circular orbits. But here I see that no matter what your initial conditions are, as long as you have two turning points and hence a bound orbit, which happens for all negative values of E, you must have a closed orbit simply because by the time you go from one apse to another, the angle turns out through pi. In fact, by the time you go from Rmin to Rmax and back again to Rmin, so you complete a cycle in the radial direction, theta changes by twice pi, and so you are exactly back where you started. So the orbit is closed, and as we have just seen, one complete radial oscillation, that is from Rmin to Rmax and back again, occurs over one full turn. So this is the picture for this kind of orbit. You have a small circle here showing Rmin, a large circle showing Rmax, and the orbit essentially will go from this max to the min and back to the max in exactly 2 pi change of theta, which means you will go back exactly here. Now, this particular integral that we evaluated here, of course, I could just tell you that this is a standard integral and you can look it up in any textbook, and that would be perfectly correct to do. I would still like to show you how this is evaluated, because the evaluation will tell us something more about this problem, the next one, and in fact a much more important problem. So let me just quickly indicate how this integral can be evaluated. In fact, we are going to evaluate this by the most direct method possible, finding out an antiderivative for this complicated looking function here, and then use that antiderivative directly to evaluate the definite integral. So not only is the definite integral something we can evaluate exactly as we did right here, we can actually evaluate this integral from Rmin to any arbitrary R we want, which will be quite useful later. For the time being, just take a look at the proof of this particular result that we used. The integral that we really are looking at is an integral from a to b, where a is basically taking the place of Rmin and b the place of Rmax, of this integral dx by x into square root of x minus a into b minus x. Now, if you know how to evaluate this integral, well, you can skip the next few minutes. But if you don't, I would suggest you should stick around. So what we do is carry out a very standard substitution. B minus x over x minus a, we are going to call u. And simply adding 1 to both sides tells you that b minus a divided by x minus a is equal to u plus 1. And therefore, x is simply a plus b minus a by u plus 1. Dx, the derivative, is simply minus b minus a by u plus 1 whole square du. And what is important is that when you go from x equal to a to x equal to b, u goes from infinity to 0. So the integral limits should change from infinity to 0. But because of the extra minus sign in dx, we can absorb that and change that back to 0 to infinity integral. So the integral that we need to evaluate simply becomes an integral from 0 to infinity of b minus a du by u plus 1 whole square, that's nothing but dx. The minus sign has been absorbed, as we said, in switching the limits of the integral. Then you have square root of b minus x by x minus a, that's just square root of u. And then square root of x minus a whole square, or just x minus a, which is nothing but b minus a by u plus 1, as you can see. And finally, you have a factor of x. Now, this whole thing looks pretty complicated, but if you look at it, the u plus 1 whole square will cancel with this u plus 1, the b minus a's will cancel, and in fact, you can multiply u plus 1 through by this, and you simply end up with a times u plus b. So this is actually the integral that you need to do. So one very simple substitution, that of b minus x over x minus a equals u, changes this to a rather simple looking integral. And now you would make another substitution, which at this stage should be pretty obvious. You change u to phi, where u is given by b by a tan square phi. Of course, the limits of the integral will now go from phi equal to 0 to phi equal to pi by 2. But now, with this substitution, du is simply b by a into twice tan phi into sec square phi d phi. That's what you put on the numerator here. But what about the denominator? Root u is simply root over b by a tan phi. And what is important is au plus b is simply b tan square phi plus b. If you take the b common out, you get b times sec square phi. And that simply means that you have a lot of cancellations. All the phi dependent terms here just cancel out, and you are left with twice 1 over root over ab times this integral 0 to pi by 2 of d phi. A very, very simple integral indeed. So, the important point is, even if the limit had not been pi by 2, I would still have been able to evaluate this integral, which is something we will need later. For the time being, it's very easy to see that the integral works out to be pi over square root of ab, which is the result that we had used a while ago. Let us now return to calculating apsidal angles, and this time we are going to do this for another potential. This is a three-dimensional harmonic oscillator, and the potential is simply k r square. Of course, we would usually like to write this as half m omega square r square, but here it's really the r square dependence that's important, so I am just writing k r square for that. So the effective potential will simply be this actual potential plus L square over 2 mu r square. And this is always positive and goes up to infinity on both sides. And as we have already seen in the last lecture, potentials of this kind will always lead to bound orbits. So no matter what the energy is, and the energy has to be positive in this case, you are going to have two turning points, R max and R min, which are actually solutions to this equation, E minus k r square minus L square by 2 mu r square equals 0. Now, as opposed to what we had in the case of the inverse R potential, this one gives you a quartic equation, minus r to the 4 plus E by k r square minus L square by 2 mu k equals 0. Of course, to arrive at this, from this one, we had multiplied through by r square and divided by k. So here, this is really a quartic, but actually a quadratic in r square. And so we get r max square minus r square into r square minus r min square. The sign here has been taken so that you end up with a minus r to the 4 on both sides. Note that although a quartic equation should have 4 roots, and here you do have 4 roots from the looks of it, but you should realize that r can only be positive, so roots like minus r max or minus r min are simply not allowed. So you again get only 2 roots. So now the integral that you need to do, which looks quite different from the integral that we had, ultimately, after you take out twice mu k from here, simply becomes L over root over 2 mu k, integral from r min to r max of dr over r, square root of r max square minus r square into r square minus r min square. On the face of it, this looks different from what we had done before. But a simple substitution, r square equals u, will change the dr by r to half du by u. And once you put everything in, you will see that this is exactly the same integral that we had before, except for the fact that r max and r min have been replaced by r min square and r max square. But then, the integral, apart from the factor of half, is exactly the same. I just realized that I had written a 2 by mistake here, which of course has not been carried out to the next step. So all's fine. You get half pi L over root 2 mu k and 1 over square root of r max square r min square. But now r max square and r min square are actually roots of this particular quadratic in r square, and therefore the product is simply given by L square over 2 mu k. Plug that in, everything cancels once again, but now you have got a pi by 2. The half here simply comes from this substitution here, that dr by r is half du by u. So this time the apsidal angle is pi by 2, 1/4 of a circle, and once again the orbit is closed. But one complete radial oscillation from r min to r max and back to r min would change theta by twice this angle, by pi. That means this occurs over half a turn. By the time theta turns over a complete 2 pi range, radius goes from r max to r min back to r max twice. And this is exactly what we get from the orbit. In this case, we are dealing with a three-dimensional harmonic oscillator which is confined to a plane, and so we essentially have two oscillations of the same frequency along the x and the y axis, and we know that such a situation always gives rise to ellipses. And the major axis and the minor axis, if we chose them properly, we will get them aligned along the x and the y axis. And what you see is the r going from r max to r min back to r max by the time theta turns by only pi. And so over a complete turn, r goes from r max to r min to r max, back to r min and again to r max. So two complete radial oscillations for each complete turn. Once again, a closed orbit. Now we have seen that for the Kepler problem and for this particular problem, the simple harmonic oscillator problem, that is for minus k by r and kr square, we have closed orbits no matter what the initial conditions, not necessarily when you are close to a circular orbit. This actually brings us to a very, very important theorem. We will only indicate a part of the proof today and do a more general proof later on. The theorem is actually rather amazing. It says that these two potentials, kr square and minus k by r, are the only potentials with closed orbits for arbitrary initial conditions. Other potentials can have closed orbits. After all, if the other potentials lead to a minimum in the effective potential, you will always have a stable circular orbit. But you could have other closed orbits besides these. But these two are the only potentials for which all bound orbits, regardless of the initial conditions, are closed. For other potentials, you may get closed orbits, but you will get them only for very special initial conditions. Let me now quickly give you the partial proof for this theorem that we have been referring to. The steps of this proof essentially follow closely what we did at the beginning of this lecture when we tried to show that the orbits for the Kepler problem close to circular ones are all closed. We are essentially going to do the same thing now, but for an arbitrary potential. Note that a circular orbit is possible only if the energy is exactly equal to u0, which is the minimum for the effective potential. And given the fact that effective potential is given by u plus L square by 2 mu r square, a formula which you are all familiar with by now, the minimum is given by calculating the derivative and setting that equal to 0, and this tells us that the derivative of the actual potential u at the radius of the circular orbit r0 must be equal to L square by mu r0 cube. Now, when E is very close to u0, slightly more actually, r stays close to r0 and you can effectively change the effective potential to a quadratic function, essentially doing a Taylor expansion. So U effective R is approximately given by the value U0 plus 1 by 2 factorial second derivative of U effective at R0 times R minus R0 whole square. Of course, higher order terms are there which are being neglected. And this tells us that the radial time period, the time period for radial oscillations from Rmin to Rmax and back to Rmin is given by 2 pi square root of mu divided by U double prime effective at R0. This of course is the formula with which we ended the last lecture and essentially began this one. And at the beginning we also did this, but for the Kepler potential, but this works for every kind of potential. Time period for one complete rotation, that is theta, to go from 0 all the way to 2 pi is given by 2 pi by theta dot approximately. The approximation comes in because if you are not at a circular orbit, then theta dot of course is a variable. But we are actually replacing this by the angular velocity for the circular orbit. That is L by mu R0 square. And this is what t theta works out to be. And therefore, the ratio between these two time periods, which remember should be rational for us to get a closed orbit, is given by the square root of L square over mu R0 to the power 4, U double prime effective R0. And since L square by mu R0 cube is U prime at R0, this is what our expression becomes. And since we have been talking about the apsidal angle over the last few minutes, let me just point out that the apsidal angle for a near circular orbit will be given by this expression. Half of this ratio times 2 pi. Half because the apsidal angle is after all the angle between lines joining the center to nearby successive apses. So basically a line joining a point at R minimum to one at R maximum. So not a complete radial oscillation but only half of it. So theta here works out to pi times square root of U prime R0 by R0 U double prime U effective at R0. Now this essentially is the formula that we are looking for, but let us just change this to a formula which involves only the U and not the U effective. Since U effective is given by this expression, U prime effective of course is its derivative, something which we have already used before. U double prime effective at R is simply U double prime R plus 3L square by mu R to the 4. So at R0, where we need this expression, R0 times U double prime F at R0 is simply given by R0 times U double prime at R0 plus 3L square by mu R0 cube, which is of course 3U prime at R0. So finally our expression simply becomes, for orbits close to the circular one, the ratio of these two time periods, written now entirely in terms of U, is given by square root of U prime R0 by R0 U double prime R0 plus 3U prime R0. Or we can just use the same expression to write theta A, the apsidal angle, as pi divided by capital omega, where capital omega is nothing but the reciprocal of this. R0 U double prime R0 plus 3U prime R0 by U prime R0. Of course, that's capital omega square. Omega is the square root of that. Now note that for a bounded orbit to be closed, we must demand that this omega be a rational number. Of course, the quantity in here is being evaluated at R0, the radius for the circular orbit. However, you should also realize that the use of the article the for circular orbit is really rather misplaced. A circular orbit for a potential like this occurs whenever you have a minimum of the effective potential, but that means that the radius of the circular orbit depends on not only the potential u, but also on the value of the angular momentum. By varying the angular momentum continuously, you can change the radius of the circular orbit and hence this quantity continuously. But if we want all orbits, at least all bound orbits, to be closed, we would demand that this quantity stays a rational number no matter how you change your L. That implies that this quantity must be a constant no matter what R you use this for. And of course, because omega has to be a real number, you demand that this constant be a positive constant. The argument here, of course, is that between any two rational numbers, no matter how close, there are an infinite number of irrational numbers. So it is not possible for you to have omega which is rational throughout to change from one rational value to another rational value. It has to stay at the same value throughout. Now this, of course, puts an immense restriction on the potential. This simply tells you that u double prime r by u prime r, which is nothing but the derivative of log of u prime r with respect to r, is given by c minus 3 over r, and this is immediately solvable, and you end up with this result. U prime r has to be k times r to the power c minus 3, where k is a constant of integration. And u of r is an integral for this, and you end up with k by c minus 2 r to the c minus 2. So, at least for all nearly circular orbits to be closed, irrespective of the initial condition, as long as you are close to a circular orbit, if you want the orbit to be closed, the potential must be a power law potential. It must be some power of r. No other form works. And this power law potential can be written as k by alpha r to the alpha, where alpha is greater than minus 2. And in order that this potential be attractive, you want k to be positive, irrespective of whether alpha is positive or negative. Note that if alpha is negative, the magnitude of the potential will decrease with r, but you want the potential to increase when you increase r. And that's exactly what happens even in that case, because then the k over alpha, constant in front, is negative, just like our minus k by r. Of course, with this restriction, it's easy to see that the two special potentials for which we had demonstrated that not only for orbits close to the circular, for all bounded orbits, you have closed orbits, namely alpha equal to minus 1 and alpha equals plus 2. They definitely fit into this pattern. But now let's come to the question about whether you can have other potentials. The important demand, of course, is omega has to be a rational number. But if you have u given by this, u prime and u double prime are easy to calculate. And if you just plug this all in, omega works out simply to be square root of alpha plus 2. So not only must our potential be a power law potential with a power r to the alpha which is more than minus 2, you must also have square root of alpha plus 2 as a rational number. Now, the obvious cases where omega turns out to be rational happens to be alpha equal to minus 1, where omega works out to be plus 1, and alpha equals 2, for which omega works out to be plus 2. Note that these are the cases where we have actually calculated the apsidal angles explicitly for all initial conditions, and we have already seen that all bound orbits are closed for these potentials. Indeed, the apsidal angles of pi and pi by 2 for these two potentials are also things which we had already calculated. However, this does not complete the proof of Bertrand's theorem though. Our argument so far, which only invokes looking at orbits close to the circular, does not rule out, say, other values, for example, alpha equal to 7, or 14 or 34 would have given rise to closed orbits close to the circular. Not only that, things like alpha equal to 0.25, which will give omega as square root of 2.25, that is 1.5, or alpha equal to minus 0.04. All of these would also give you rational values of omega, and our calculation so far does not rule them out. But that is because we are now looking at only orbits which are close to circular. To complete the proof of the theorem, we must take a look at all initial conditions, and that is what we are going to do in a later lecture. But the basic idea has already been conveyed here. In the next lecture, we will take a look at our formula for calculating theta of r, not only for the apsidal angle, but for the full trajectory, and work it out explicitly for the Kepler problem. Then we will go on to see that there are other, perhaps simpler means of figuring out the orbital equation, which will also serve as a way of figuring out the force law if the orbital equation is given. Bye till then.